Welcome back. So we're just working our way through the continuum theory protocol. Let me remind you of that. So we've done various pieces in this, and sorry, there's a lot of notes here. Um, so what have we done thus far? Well, the first thing we did was we talked about what are the field variables, velocity. Then we impose the conservation law in the form of force balance, F equals ma, which another way of saying it is that the rate of change of linear momentum is equal to minus the divergence um, of the stress tensor. Well, sorry, minus the divergence of the flux of linear momentum. And then we talked about the Newtonian fluid constitutive assumption. And the objective now is step 4. We want to derive the governing field equation. And the way we do that is we already have our force balance, which I've shown here in green. We now have our constitutive model, which I show here on the right. And by bringing those two together, we can end up with the relevant partial differential equation that describes the motion of the fluid. And this is we've done this 3 or 4 times now, where we obtain governing equations in the form of partial differential equations that describe our material, and that's really powerful. So the force balance can be written in either of these two ways. So I just reviewed this, and I'm just pointing out, that this piece right here is the MA part, and this piece is the force, which is given by basically the divergence of the stress tensor, if you like. So it's given really by the gradients in stress. And so now, in order to make progress with this, it's really clear what we need to do. What I need to do is I need to take this expression right here and stick it into the divergence of the stress, or this expression for the gradient. So I note that sigma ij can be rewritten in this form. This is going to be useful for us. And hence, what I have when I want to evaluate d sigma ij by dxj, that's the thing I want to evaluate. So let's just be clear. I'm just following the instructions. This is d by dxj, and this part is sigma ij. So I have 3 terms that I need to take the derivatives of. So the first one is d by dxj on minus p delta I delta j. Note, I know every time I do one of these things that I have one free index, which is I. Okay, so that's the thing you want to be keeping track of. You know that I'm going to be summing over j, and I want to have the final free index and I, because it's basically a vector equation, right? Why do I say it's a vector equation? Because this equation that I write right here, there's 3 equations, really. There's rho dv1 by dt, there's rho dv2 by dt, and there's rho dv3 by dt. Those are the 3 components of velocity, and I'm trying to find out what the dynamics of those components is. So the first term is relatively modest, because it instructs us to take the xj derivative with respect to the pressure. Delta ij doesn't depend on space. It's a number. It's a number multiplying p, but p can depend on space. And so I take the xj derivative of p, which you see here, but then I follow the instruction, which is sum over all j. And what that means is that only time that the sum over j will fire is when j is equal to I, because then the Kronecker delta will be non-zero. So I'm left with minus dp by dxi. So that's the result for the first of those terms. We're good. That's all there is to it. Okay, the second term. That one says we're going to take the xj derivative of dvi by dxj. So once again, I just follow the instructions of what it means to take a derivative, and I end up with this expression. Notice that there is a sum over j. The only free index is I, as it should be. So this, I already recognize it as the Laplacian, but let's actually just make sure. So let's sum over j. So that's what I do here. So d squared vi by dx1 squared plus d squared vi dx2 squared plus d squared vi dx3 squared. That is the Laplacian of the ith component of the velocity. So that's good. So we see that the second term, so what do we have thus far? We have minus dp by dxi. We've had eta d squared vi, Laplacian vi. This basically is a statement of, you recall this from the diffusion equation. This is basically, as I said before, it's diffusion of momentum. It's diffusion of velocity. It's diffusion of velocity because there's regions with higher velocity and regions with lower velocity, and so they're coupled by this sort of diffusion thing. And then the last term is this one. So that one's interesting because I can switch the order of the j and the x derivatives, and what I'm left with is eta d by dxi of dvj by dxj. This thing is the divergence of the velocity. So I will probably do something on this in upcoming vignettes, but for the moment, all I really want to say about that is that for an incompressible fluid, one that you can't really squeeze, then the divergence of velocity is 0. And so we can now put everything together, which I do right here. So basically what I've said is that the rate of change of the I component of velocity is given by minus the gradient in the pressure plus eta times the Laplacian of VI. So this is the Navier-Stokes equations, which can be rewritten as I say right here. So what we've done, is we've followed the continuum theory protocol. We've done the 4 steps. We identified the field variables, namely the velocity. We did the conservation laws or the balance laws, and that was fine. And then from there, we figured out what the constitutive model was, which was the stress is related to the velocity via the Newtonian fluid assumptions. And then the 4th point was we worked out what the field, the governing equations are, and there they are in the box before you in all their glory. So that is the Navier-Stokes equations. And, it's a really beautiful and deep topic that allows us to think about all sorts of different things. And, if you find yourself aggravated or confused or whatever, just keep on reminding yourself that this is basically F equals ma. That's the key point.